Hi, we are Team Dysprosium, and we would like to talk about the language of analytical chemistry. First and foremost, today we will talk about an important topic in the language of analytical chemistry, which is the analysis, measurement, and determination. We can say that analysis is conducted to determine the identity, concentration, and properties of an analyte. In other words, it offers chemical and physical information about the sample. We can also define determination as a means to know the chemical and the physical information about the analyte. We must measure its physical or chemical property to do so. First, we should learn some terms and definitions. So, an analyte is the component in the sample interest, while a matrix is the remainder of the analyte. As an example, I would like to introduce Morse method in determining chloride ion concentration in a solution. So, this method can be used to determine the chloride ion concentration of water samples from many sources, such as stream water, river water, and more. Our titrant is silver nitrate, and our indicator is potassium chromate. Once you perform this titration, you will notice that the endpoint is indicated by a red-brown precipitate of silver chromate. Therefore, in Morse method of chloride ion determination, our analyte is the chloride ions in a water sample, while the matrix is the rest of the sample. Now we have some examples on methods used to identify and quantify analytes. Let's differentiate first the classical and instrumental methods. Classical methods does not depend on mechanical or electronic instruments other than a balance. Meanwhile, an instrumental method depends on the instrument of a physical property of the analyte. So for the classical method, we have a flame test, which is used to check if an element is present in an analyte by exposing it to flame and observing the change in color of the flame. For titration, the reactant is added to the analyte until an equivalence point is obtained. Now, let's see the instrumental methods. We have spectroscopy, which measures the interaction between electromagnetic radiation and the atoms or molecules belonging to a sample. Then we have pH determination, which we all know this. It measures how basic or acidic a solution is. Now I'm going to propose a question. I'm going to give you 10 seconds to answer this question. What is the analyte and matrix in this situation? Estimation of carbon dioxide in fumes emitted by an industrial plant. Time's up. So the answer to our question earlier is that the analyte for our situation is carbon dioxide, while the matrix is fumes.
Now let's talk about accuracy versus precision. Accuracy is how close a set of measurements are to the real value, while precision is how close a set of measurements are to each other. Here are some of the few examples that show the difference between precision and accuracy. Here are the different testings of pH values with the true value being pH 7. In high accuracy and precision, the values are near to each other and linked to the true value, while in the precise only trials, the pH values are near to each other but far from the true value, while in the accurate only, the pH values are near to the true value but far from each other. And lastly, in the low accuracy and low precision, the pH values are not only far from each other but also nowhere near from the true value. Now, let's talk about selectivity versus sensitivity. Sensitivity is the measure of a method's ability to distinguish between two samples, reported as the change in signal per unit change in the amount of analyte. Sensitivity is often confused with method's detection limit. The difference is that MDL is the smallest amount of analyte that can be determined with confidence, while sensitivity gives us the smallest amount of analyte that can be detected between two samples. Meanwhile, selectivity is a measure of a method's freedom from interferences, as defined by the method selectivity coefficient. An analytical method is selective if its signal is a function of only the amount of analyte present in the sample. It is when k is greater than plus 1 or less than negative 1 that it indicates that the method is more selective for the interferent than for the analyte.
At this point, we will discuss the factors to consider in selecting an analytical method And what is analytical procedure development? An analytical method is a qualitative or quantitative approach to studying something in a detailed and intelligent manner to reach conclusions. To further understand the analytical methodology, let's define and differentiate its levels. First is technique. A technique is any chemical or physical principle that we can use to study an analyte. And then we have the method, which is the application of a technique for a specific analyte in a specific matrix. Next is procedure, or the set of written directions that tell us how to apply a method to a particular sample, including information on how to collect the sample, how to handle interferences, and how to validate results. And lastly, protocol. A protocol is a set of guidelines that specify a procedure that an analyst must follow if an agency is to accept the results, most commonly results of an analysis that supports or defines public policy. Take this example of lead concentration determination in drinking water. In this case, the technique used is the graphite furnace atomic absorption spectroscopy. This technique uses the chemical principle of atomization and the physical principle of light absorption. The methods used for determining lead concentrations in soil, water, and blood samples differ. Also, a method may have several procedures as each analyst or agency adapts it to a specific need. In this example, the American Public Health Agency and the American Society for Testing Materials published separate procedures of lead determination. And lastly, when determining the concentration of lead in drinking water under the Safe Drinking Water Act, for example, the analyst must use a protocol specified by the Environmental Protection Agency. Let us now talk about analytical method selection. It is best to note that best method reflects the best results. The analytical method selected needs to have adequate performance characteristics. These characteristics are summarized as reliability criteria, and the other is the practicability criteria. The source of signal, proportionality constant, and the ease of handling the samples affect the method's accuracy and precision. The accuracy of a method is preferably determined by the analysis of standard or certified reference materials that have been analyzed by a group of skilled analysts using several compatible methods to provide certified values together with the confidence limits of that value. For precision, strictly speaking, it is imprecision that is measured by carrying out replicate analysis on the same homogeneous and stable sample, where the standard deviation or the spread of the analytical values is calculated. In selecting a method, the ideal is to combine high precision with high accuracy. Moving on to the next, we have detectability and sensitivity. Detectability is defined as the minimum concentration of analyte that can be detected. On the other hand, sensitivity is the slope of the response concentration curve or line. If the slope is steep, the method has a high sensitivity, whereas shallow slope indicates low sensitivity. When a narrow range of concentration is of interest, a high sensitivity is often desirable, while for a wide range of concentrations, low sensitive methods may be preferable. Next, specific methods show signals in response to a particular analyte in the matrix. Selective methods, on the other hand, are methods that are able to discriminate a particular analyte in a complex mixture without interference from others. Highly specific and highly selective methods are preferred. However, many methods are semi-specific, which rely on the absence of interfering substances. Sometimes, a method with poor specificity is acceptable when the purpose of the analysis is to measure all similar substances within a group. Robustness and ruggedness are something to consider in method selection. This attribute refers to the capacity of a method to perform adequately amid small changes in the experimental conditions. Such fluctuations could include the timing of stages, changes in temperature, or the precise concentrations of reagents. It also includes variations in the skill, training, and experience of the analysts carrying out the method. Another way to narrow the choice of methods is to consider three potential limitations: the amount of sample available for the analysis, the expected concentration of analyte in the samples, and the minimum amount of analyte that will produce a measurable signal. In other words, scale of operation takes into account how large the samples will need to be and if they are capable of being carried out on the technique used. Finally, analytical methods can be compared in terms of their need for equipment, the time required to complete an analysis, and the cost per sample. Methods relying on instrumentation are equipment intensive and may require significant operator training, while other methods only require simple equipment and reagents and can also be learned quickly. The time required to complete an analysis for a single sample must also be thought through, especially that the number of samples that can be analyzed per hour differs substantially from method to method. Lastly, the cost of an analysis, including the cost of necessary equipment and reagents, also the labor, and the number of samples that can be processed per hour is considered. In general, methods relying on instruments cost more than other methods. Last is making the final choice. The aforementioned criteria are not mutually independent. Usually, the most important design criterion is accuracy, and the best method is capable of producing the most accurate results. The best method is often dictated by the sample's properties. Generally, method development comes into play when changes to already established protocols are needed to make them more effective or improve the accuracy of the analysis. The process starts by defining what you want to measure and determining how to go about measuring it, then putting your new methodology to use by testing it on samples that have already been analyzed using other methods. Sometimes, theoretical calculations are necessary to predict the results of the experiments. And for the last step is, of course, the testing of the design process. In developing a procedure that accomplishes our goals for the analysis, we give attention to compensating for interferences, to selecting and calibrating equipment, to acquiring a representative sample, and to validating the method. A method's accuracy depends on its selectivity for the analyte, but it may not be free from interferences from the sample or agents. When the sample is free of interferences, the total signal is a sum of the signal due to the analyte, or SA, and the signal due to interferences in the reagents, or SRH. To solve an equation for analyte concentration, an independent determination of SRH is necessary. To measure the contribution of reagents, use a method blank or reagent blank, a solution that does not contain the sample. However, method blanks cannot compensate for interferences in the sample matrix. If we happen to know the interferences identity and concentration, then we can add it to the method blank. But this is not a common circumstance, therefore we find a method for separating the analyte and interference before continuing the analysis. For selecting and calibrating equipment, quantitative analytical methods convert the signal into the amount of analyte in a sample using the proportionality constant, or Ka. Total analysis method uses stoichiometry, while concentration methods use complex experimental conditions. Calibration is the process of experimentally determining the value of Ka by measuring the signal for one or more standard samples, each of which contains a known concentration of analyte. When using several standards with different concentrations of analyte, the result is best viewed visually by plotting SA versus the concentration of analyte in standards. Such a plot is known as a calibration curve. Next, proper method selection and execution ensure accurate analysis. Proper sampling strategy ensures samples are representative of the material. Sampling errors lead to errors in accuracy, and such errors are biased or non-representative sampling and contamination. Note that sampling errors are independent of analytical method errors and can't be corrected by reagent blank evaluation. Lastly, validation is a crucial process for demonstrating confidence in a procedure by ensuring the appropriateness of its precision and accuracy for the problem, and that the procedure has sufficient detail for comparable results. In the absence of standards, accuracy can be evaluated using known methods. Analytical method development does not necessarily mean creating and adapting a brand new technique, but rather improving upon existing ones.
Good day, I am Trisha and I will be presenting the basics of quality assurance. Quality assurance in general is a broad plan for maintaining quality in all aspects of a program, including all quality control measures such as sample collection, sample analysis, data management, documentation, and evaluation. QA prevents and detects quality problems. Meanwhile, in a business setting, quality assurance at its core involves a set of activities designed to guarantee the quality of a product or service. It encompasses quality planning, quality control, and quality improvement. The main importance of quality assurance lies in its ability to provide confidence to customers that they are receiving reliable and satisfactory products or services. Quality assurance is essential for organizations to build trust and maintain customer loyalty. When customers have confidence in the quality of a product or service, they are more likely to make repeat purchases and recommend the organization to others. This in turn leads to increased customer satisfaction and brand reputation. QA or quality assurance ensures that development and or maintenance processes are adequate for a system to meet its objectives. Typically, its principles are to develop and validate methods for analyzing and producing products to ensure that they meet specifications. Document those methods in standard operating procedures like SOPs and production records. Also, to assist quality control staff with troubleshooting and resolving unusual problems, to develop quality metrics and assess trends for products or process implications, to also develop and implement improvements to existing sample and data analysis techniques. It also includes evaluating current processes and identifying ways to save time and money without sacrificing product quality. It also aims to investigate product and process deviations, identifying the root cause, and develop corrective and preventive actions. Quality assurance also involves management systems maintenance, like the ISO 9001 and ISO 17025. ISO 17025 was introduced in 1999 by the International Organization for Standardization or ISO and the International Electrotechnical Commission or IEC as an internationally recognized standard for laboratory competence. But what is the difference in value between the two standards? And does having the ISO 17025 accreditation mean that you also need ISO 9001 certification? The main difference between ISO 17025 and ISO 9001 is that um, ISO 9001 applies to all kinds of businesses in all types of industries and sectors. ISO 17025 only holds value for businesses that include testing and calibration laboratories such as pharmaceuticals, cosmetics, universities, and etc. ISO 9001 is a quality management system that will allow your business to keep records, set policies and procedures, and organize production. The ISO 7025, on the other hand, is an accreditation differs because it stores necessary measurements and records that your business may need to create an efficient and effective process. There are also some mathematical equations that we can use to assess the quality of products. And here we will explore some commonly used quality assurance formulas. And one of them is the defect rate. The defect rate formula is widely used in quality assurance to measure the proportion of defects in a given sample. It helps organizations assess the quality of their products or services by calculating the percentage of the defects in relation to the total unit tested. This formula provides valuable insights into the overall quality performance and helps identify areas for improvement. Here we have an example of a defect rate problem. In a sample of 500 test specimens for a new medical diagnostic kit, 15 were found to have inaccuracies or faults. Calculate the defect rate as a percentage using the defect rate formula. Subsequently, analyze the results to assess the quality of the diagnostic kits, considering industry standards and the desired level of precision. How might this defect rate influence decision making regarding the production process or the need for further quality control measures in the laboratory? To calculate the defect rate, we will use the formula defect rate in percentage is equals to the number of defects over the total unit tested multiplied by 100. For the given example, we have a number of defects of 15 and total units tested 500. And substituting the values, we will get 3%. This means that 3% of the tested specimens were found to have inaccuracies or faults. The laboratory should interpret this defect rate in comparison to industry standards and desired level of precision to make informed decision about the quality of the diagnostic kits and whether adjustments to production process or additional quality control measures are necessary. Here we have a practice problem. Pause the video if you need more time to calculate the problem. Suppose a manufacturing facility produces electronic components and the quality control team examines a random sample of 800 units. Within the sample, they discover various types of defects in 35 units. Calculate the overall defect rate as a percentage using the defect rate formula and then discuss the implications of this defect rate on the quality management system. Additionally, consider how this information might influence decisions regarding production processes and the need for more targeted quality improvement initiatives. To calculate the defect rate, we will use the formula d or percent is equals to number of defects over the total unit tested multiplied by 100. From the given example, we will be substituting the 35 units defect over the 800 total units tested multiplied by 100 and we will get 4.375%. Now, in terms of implications for the quality management system, a defect rate of 4.375% suggests a noteworthy proportion of units with defects. This may signal the need for a thorough examination for the production processes, supplier quality, or material inputs. The quality control team should consider implementing targeted improvements such as enhanced testing protocols, process adjustments, or employee training to bring the defect rate within acceptable industry standards. This information is necessary for informed decision making to maintain or enhance the overall quality of the electronic components produced in the manufacturing facility. Here we have another mathematical equation that we can utilize to assess the quality of our products, and that is the failure rate. Failure rate formula is essential in quality assurance for evaluating the reliability of products or services. It measures the rate at which failures occur during a specified period. Considering the total operating time by calculating the failure rate, organizations can identify potential weaknesses and take proactive measures to improve reliability. Here is an example of a failure rate problem, and I'll read it first. In a chemical laboratory, a research team is conducting experiments on a new reaction process. Over a period of 500 hours of continuous testing, 8 instances of equipment failure occurred. Calculate the failure rate per hour using the failure rate formula. Subsequently, discuss the implications of this failure rate on the reliability of the equipment in the laboratory, and consider how it might influence decisions regarding maintenance schedules or the need for equipment upgrades. To calculate the failure rate per hour, you can use the formula failure rate equals to number of failures over total operating time. From the given example, we have 8 number of failures and 500 total operating time. And dividing the two, we will get 0.016 failures per hour. Now, considering the implications, a failure rate of 0.016 failures per hour indicates a relatively low occurrence of equipment failures. However, The laboratory should assess this rate in the context of the criticality of the experiments being conducted. If the experiments are highly sensitive or time critical, even a low failure rate may have significant consequences. This information can guide decisions about equipment maintenance schedules, potential upgrades, or adjustments to experimental procedures to enhance reliability and minimize disruptions. Here we have another example for the failure rate, and you can pause the video if you need more time to answer. In a nuclear power plant, a safety assessment team is analyzing the failure rate of a critical component in the reactor system. Over a monitoring period of 3,000 hours, 5 instances of component failure were recorded. Calculate the failure rate using the appropriate formula for failure rate. Subsequently, discuss the implications of this failure rate in the context of nuclear safety. How might this information influence decisions regarding maintenance schedules, system upgrades, or safety protocols to ensure the continued safety and reliable operation of the nuclear power plant? To calculate the failure rate in this nuclear power plant scenario, we could use the formula failure rate is equals to number of failures over the total operating time. In this case, as being mentioned from the problem, they have recorded 5 operating failures, and their operating time is 3,000 hours. And dividing the two, we will get 0.00167 per hour. And this value suggests a relatively low frequency of component failures in the nuclear power plant. However, in the critical context of nuclear safety, even low failure rates can have significant implications. Um, this information could prompt the safety assessment team to carefully review the potential adjust maintenance schedules, consider system upgrades to improve reliability, and enhance safety protocols, ensuring the continued safe and reliable operation of the nuclear power plant. And the failure rate data can be valuable tool for making informed decisions to mitigate risk and maintain the highest standards for safety. Last but not the least, we have the process capability index. This formula is used to assess the capability of a process to meet specified requirements. It compares the spread of process variation to the tolerance limits defined by upper and lower specification limits. By calculating the process capability index, organizations can determine if their processes are capable of consistently producing products or services within the desired specifications. Here we have an example of a process capability index problem. In a manufacturing process producing a critical component for aerospace applications, the specified diameter tolerance is set with an upper specification limit USL of 25.5 millimeters and a lower specification limit or LSL of 24.5 millimeters. The process standard deviation is determined to be 0.2 millimeters. Calculate the process capability index, and after that, um, after obtaining the CP value, discuss how this index can be interpreted in the context of meeting the specified tolerance requirements for aerospace components. Additionally, consider what actions or improvements might be necessary if the CP indicates potential issues with the process capability. To calculate the process capability index CP, we can use the formula CP is equals to USL minus LSL all over 6 multiplied by the standard deviation. From the given example, we can substitute the values 25.5 as the upper limit and 24.5 for the lower limit, and then multiply the standard deviation of 0.2 to 6, and we will get 0.833. Interpreting the safety value, ACP less than 1 indicates that the process may have some challenges meeting the specified tolerance requirements for aerospace components. In this context, it's crucial to assess whether the CP meets the desired level of process capability for the given specifications. If the CP is below the desired threshold, it may signify that adjustments or improvements to the manufacturing process are needed to enhance its capability. Another practice problem for the process capability index. A metal manufacturing company produces metal components with a specified target dimensions of 50 millimeters. The process has a standard deviation of 2 millimeters. In a recent production run, a random sample of 100 components was measured, and the average dimension was found to be 49.5 millimeters. Calculate the process capability index using the formula, and interpret the result and discuss how it informs the plant about the capability of the production process to meet the desired quality specifications. To calculate the process capability index or CP, we can use the formula CP is equals to USL minus LSL all over 6 multiplied by the standard deviation. The givens are 50 millimeters for the target dimension, 2 millimeters for the standard deviation, 100 for the sample size, and 49.5 millimeters for the average dimension from the sample. Assuming that there are no specified lower or upper specification limit, we'll consider a unilateral tolerance around the target dimension. Let's say the upper specification limit is 51 millimeters. Now we can calculate the CP. CP is equals to 51 minus 50 all over 60 multiplied by 2, and we will get 0.0833.
In this slide, we will tackle about quality control and quality assessment. Quality control encompasses all activities that bring an analysis into statistical control. The most important facet of quality control is a set of written directives describing the relevant laboratory specific, technique specific, sample specific, method specific, and protocol specific operations. These include standard operations procedure, protocol for a specific purpose, good measurement practices, and good laboratory practices. The directions for analyzing a specific analyte in a specific matrix are described by a standard operation procedure, or SOP. The SOP indicates how we process the sample in the laboratory, how we separate the analyte from potential interference, how we standardize the methods, how we measure the analytical signal, how we transform the data into the desired result, and how we use the quality assessment tools to maintain quality control. If the laboratory is responsible for sampling, then the SOP will also state how we are to collect, process, and preserve the sample in the field. An SOP may be developed and used by a single laboratory, or it may be a standard procedure by an organization such as the American Society for Testing Materials or the Federal Food and Drug Administration. As for the protocol for a specific purpose or PSP, a well established procedure for analysis needs to be adhered to accurately. There is a general outline of a protocol for a specific purpose in quality control. First is sample processing. The sample is prepared for analysis. This could involve grinding, dissolving, diluting, or other processes to make the sample suitable for analysis. The second is separation. The analyte is separated from other components in the sample that could interfere with the analysis. Third is standardization. The method is calibrated using standards, and this ensures that the method is working correctly and provides a way to convert the analytical signal into a concentration or amount of the analyte. As for the measurement, the analytical signal such as absorbance of light, mass to charge ratio, voltage, etc. is measured. Fifth is data transformation. The measured signal is converted into a result such as the concentration or amount of the analyte in the sample. Six is the assessment. Tools such as control charts, duplicate analysis, spike recoveries, and others are ensured to ensure that the analysis is in control and that the results are reliable. Good measurement practices or GMPs describe operations specific to a technique. In general, GMPs provide instructions for maintaining, calibrating, and using equipment and instrumentation. As for good laboratory practices or GLPs, this describes the general laboratory operations that we must follow in any analysis. These practices include properly recording data and maintaining records, using chain of custody forms of samples, specifying and purifying chemical reagents, preparing commonly used reagents, cleaning and calibrating glasswares, training laboratory personnel, and maintaining the laboratory facilities and general laboratory equipment. Although quality control directives explain how we are to conduct an analysis, they do not indicate whether the system is under statistical control. This is the role of quality assessment. The goals of quality assessments are to determine when an analysis has reached a state of statistical control, to detect when an analysis falls out of statistical control, and to suggest the reasons for this loss of statistical control. For convenience, we divide quality assessment into two categories: internal methods, coordinated within the laboratory, and external methods organized and maintained by an outside agency. As for internal methods of quality assessment, the most useful methods for quality assessment are those coordinated by the laboratory, providing immediate feedback about the analytical method's state of statistical control. Internal methods of quality assessment includes the analysis of duplicate samples, the analysis of blanks, the analysis of standard samples, and spike recoveries. An effective method for determining the precision of an analysis is to analyze duplicate samples. Duplicate samples are obtained by dividing a single graph into two parts, although in some cases, the duplicate samples are independently collected gross samples. We report the results for the duplicate samples by x sub 1 and x sub 2 by determining the difference or relative difference between the two samples and comparing them to an accepted value such as those shown in table 1. Alternatively, we can estimate the standard deviation using the results for a set of n duplicates is the difference between the ith pair of duplicates. The degrees of freedom for the standard deviation is the same as the number of duplicate samples. If we combine duplicate samples from several sources, then the precision of the measurement process must be approximately the same for each. As for an example, to evaluate the precision for the determination of potassium in blood serum, duplicate analyses were performed on 6 samples, yielding the following results in milligram kilo per liter. The problem states that we have to estimate the standard deviation for the analysis. You can pause this part in the video if you need more time to answer this slide. As for the solution of the problem stated, uh, first, to estimate the standard deviation, we first have to calculate the difference and the square difference for each duplicate. The results of these calculations are summarized in the following table. And then after getting the difference and the square difference, we have to calculate the standard deviation. And the answer is we have 8.4 as for standard deviation. As for a practice exercise, to evaluate the precision of a glucometer, a device a patient uses at home to monitor their blood glucose level, duplicate analyses were performed on samples from 5 individuals, yielding the following results in milligram glucose per 100 milliliter. In this problem, we also have to estimate the standard deviation for the analysis. You can pause this part so if you need more time to answer this practice problem. The answer for the practice problem is first we have to calculate the difference and the squared difference for each duplicate. Results of these calculations are summarized in the following table. After getting the difference and square difference, then we can finally calculate the standard deviation, and it is shown that the standard deviation for the practice problem is 1.08. The second internal methods for quality assessment is analysis of blanks. Blanks are samples that are processed in the same manner as the actual samples, but do not contain the analyte of interest. They are used to contamination or systematic error that might occur during the sample preparation analysis. The most common blank is a method blank in which we take an analyte-free sample through the analysis using the same reagents, glider, and instrumentation. A method blank allows us to identify and correct systematic errors due to impurities in the reagents, contaminated glassware, and poorly calibrated instrumentation. A minimum, a method blank is analyzed whenever we prepare a new reagent. Even better, the regular analysis of method blanks provides an ongoing monitoring for potential systematic errors. A new method blank is run whenever we analyze a sample with a high concentration of analyte because any residual carryover of analyte produces a positive determinate error. When we collect samples in the field, additional blanks are needed to correct for potential sampling errors. A field blank is an analyte-free sample carried from the laboratory to the sampling site. At the sampling site, the blank is transferred to a clean sample container, exposing it to the local environment in the process. The field blank is then preserved and transported back to the laboratory for analysis. A field blank helps us identify systematic errors due to sampling, transport, and analysis. A trip blank is an analyte-free sample carried from the laboratory to the sampling site and back to the laboratory without being opened. A trip blank helps us to identify systematic errors due to cross-contamination of volatile organic compounds during transport, handling, storage, and analysis. As for the analysis of standard samples are samples with known concentrations of analyte. They are used to check the accuracy of the analysis. One of the most important quality assessment tools is the recovery of a known addition or spike of analyte to a method blank, a field blank, or a sample. To determine a spike recovery, the blank or sample is split into two portions and a known amount of a standard solution of analyte is added to one portion. The concentrations of the analyte is determined for both the spike and unspiked portions, and the percent recovery is calculated as shown in the formula attached, where A is the concentration of analyte added to the spike portion. As for an example, a spike recovery for the analysis of chloride in well water was performed by adding 5 ml 5000 ppm solution of chlorine to a 50 ml volumetric flask and diluting to volume with the sample. An unspiked sample was prepared by adding 5 ml of distilled water to a separate 50 ml volumetric flask and diluting to volume with the sample. Analysis of the sample and the spike sample returned chloride concentrations of 18.3 ppm and 40.9 ppm respectively. Determine the spike recovery. For this slide, you can pause the video if you need more time to answer the question. To calculate the concentration of the analyte added in a spike, we take into account the effect of dilution, and then we get the spike recovery. The spike recovery for the problem is 90.4%. As for a practice exercise, to test a glucometer, a spike recovery is carried out by measuring the amount of glucose in a sample of a patient's blood before and after spiking it with a standard solution of glucose. Before spiking the sample, the glucose level is 86.7 milligram per 100 ml, and after spiking the sample, it is 110.3 milligram per 100 ml. The spike is prepared by adding 10.0 ml of 25,000 milligram per 100 ml standard to a 10.0 ml portion of the blood. What is the spike recovery for this sample? If you need more time to answer this question, you can pause the video. As for the answer to the said question, adding 8 ml spike to a 10 ml sample is a 1,000-fold dilution. Thus, the concentration of glucose is 25 milligram per 100 ml and the spike recovery is 94.4%. Internal methods of quality assessment always carry some level of suspicion because there is a potential bias in their execution and interpretation. For this reason, external methods of quality assessment also plays an important role in quality assurance programs. One external method of quality assessment is proficiency testing schemes. These are inter-laboratory comparisons coordinated by an external agency. In these schemes, multiple laboratories analyze the same sample and their results are compared to each other. This allows laboratories to assess their performance relative to others, which can help identify areas for improvement. The second, the second external method for of quality assessment is interlaboratory comparison or collaborative trials. These are studies where several laboratories measure the same samples to assess the performance of a particular method or to establish the reference value of a material. They provide information on the reproducibility of methods and can be used to validate methods. And lastly is the use of certified reference materials or CRMS. CRMS are materials with property values that are certified by a technically valid procedure. They provide a reference point against which other materials can be compared. CRMS are used to calibrate instruments, validate methods, and assign values to materials. These methods provide a way for laboratories to compare their performance with others and to identify and correct problems that may not be apparent from internal quality control alone.